Yep. And how do I go from there?
So I'll bring this up, and then you can.
Okay, and how do I advance it?
So
Okay, the title of our paper is Survival of Cyanobacteria in Rivers Following their Release in Water from Large Headwater Reservoirs. I'll start off the presentation, and then my colleague Nick, who's our fluid mechanics expert from Sydney University, will finish it for us. So, cyanobacterial blooms in large headwater reservoirs can pose problems when releasing water downstream. If you release the surface waters, you can end up with contamination downstream if the warm bloom-infested waters are released and the bloom travels downstream and contaminates the river downstream. Alternatively, if you can select cold bottom hypolimnetic water, then you'll have low cyanobacterial presence, but you run the risk of cold water pollution downstream. However, if cyanobacterial die-off in rivers is rapid, it may be possible in some instances to actually release the contaminated surface waters, and the cyanobacteria will then die off, and you can avoid cold water pollution issues. So our study considered factors which lead to cyanobacterial survival, or alternatively their rapid die-off in rivers downstream of large headwater reservoirs. We looked at 5 rivers in New South Wales. Initially, the Murray and Edward rivers in the south of the state. The Macquarie River downstream of Boundong Reservoir, the Cudgegong River downstream of Windermere Reservoir, and finally the Hunter River downstream of Glenbourne Reservoir. So they were our study sites. We obtained cyanobacterial data for the years when blooms were present in the headwater reservoirs and also the rivers. We obtained flow data, water depth data, the bed gradients and river cross-section data, and these were used to estimate the turbulent strain rate experienced by the suspended cyanobacteria in the water. And the river geomorphology was obtained from previous river styles reports done by my previous employer, DPI Water, plus its predecessors, and also the extent of gravel riffle reaches was measured from aerial photographs. In terms of geomorphology, the 5 rivers have quite variable differences in geomorphology. In particular, the Murray and Edward rivers are laterally unconfined rivers with wide floodplains and have beds of fine-grained sediments. We only measured about 20 kilometres of riffle in the Murray, and the bed gradients in the Murray were about 20.5 centimetres per kilometre immediately downstream of Ume Reservoir, and as low as 7.8 centimetres per kilometre further downstream around Swan Hill. And for the Edward, the average bed gradient was around 10 centimetres per kilometre. So very flat rivers. The Macquarie River is partly confined in the valley setting and has gravel and sand beds mainly, with about 7.5 kilometres of riffle. The bed gradients there were a little bit steeper. They varied from 52 centimetre per kilometre just downstream of Boundong Reservoir down to around 26 kilometre further downstream at Warren. The Cudgegong and the Hunter rivers were also partially confined in the valley setting, but had bedrock and gravel beds and generally formed series of pools and riffles. And the bed gradient in the Cudgegong over the study area was about 128 centimetres per kilometre, and the Hunter was even steeper with a bed gradient of 190 centimetres per kilometre in the upstream section. In terms of hydrology, the blooms always occurred during periods of low flow, in particular those in the Murray, the Edward and the Macquarie rivers. So these show the hydrographs in the Murray and Edward rivers in the 2009, 2010, 2016 blooms, and you can see the horizontal lines are the average monthly flows for the previous 20 years. So the flow was in those rivers was considerably curtailed during the bloom periods, as it was in the Macquarie River during the bloom there in 1998. In Windermere, the flow is regulated by irrigation demand downstream. So, but also in the Hunter, the blooms were only present when it was very low flow as well. In terms of cyanobacteria in the Murray and Edward rivers over the 3 bloom periods, there were three taxa looked at during these periods, and you can see for the most part the taxa extended well downstream from the headwater reservoirs at Hume Reservoir and Lake Mowala, certainly as far as Swan Hill, which is 789 kilometres downstream from Lake Hume. Deniliquin and Moolamine sites are on the Edward River, with Moolamine being 659 kilometres downstream from Hume Reservoir. And in many instances, the blooms were quite severe and exceeded the recreational red alert levels in place for Australia under the National Health and the NHMRC, National Health and Medical Research Association Council. So in these 2 rivers, certainly cyanobacteria survived for a long way downstream. And there's a similar story with the cyanobacteria in the Macquarie River during the bloom in 1998, with both Microcystis and Dolichospermum surviving in especially Microcystis surviving a considerable biomass, at least as far as Narromine, which is 184 kilometres downstream of Boundong Dam, and some through as far as Warren, which is almost 300 kilometres. The other two remaining rivers, the story is entirely different. As you can see in the Cudgegong, the 3 species used as examples there, and we actually had 6 species that we looked at, and it all shows the same pattern. A rapid decline in the cyanobacterial presence with distance downstream. So in fact, in the Cudgegong River, most of the cyanobacteria had actually disappeared by Melrose, which is only 19 kilometres downstream of Windermere Dam. And a similar story in the Hunter with Microcystis, Dolichospermum and Aphanizomen all disappearing quite rapidly, and most had gone by broad crossing, which is only 8 kilometres downstream. So some rivers we've had survival for many kilometres downstream. Other rivers die off very rapidly. So to try and explain some of this, we turned to some fluid mechanics, and I'll now hand over to Nicholas.
Thanks, Lee. So you'll have to forgive the equations. I'm an engineer. I just can't help myself. So my role here was to take some of Lee's data that he'd gathered over quite a few years and estimate the turbulence in the river systems and correlate that with change in algae biomass. So what we're interested in doing is sort of quantifying what the turbulence is, and we've done that by the turbulent strain rate. So the turbulent flow is one which was very mixed up, and you get large instantaneous velocity gradients. Those velocity gradients are directly proportional to the stresses on the algae cells. So this is the velocity gradients are just the strain rate. So This is our predictor, and this is what we're comparing with the algae biovolume. So this quantity here is proportional to, or the square root of the dissipation rate. Now, that dissipation rate is something that is varying enormously from the bed of the river to the free surface, and also along the length of the river, and also in time. So it's a tricky thing to try and quantify, and with sparse field data, this is quite a problem. So we just had to come up with something, and what we've got really is estimates of the dissipation rate at the gauging stations along the river, and we've done two different measurements. One of them is just this, what we call the turbulent strain rate, which is an estimate at the gauging station saying the flow's in local equilibrium there. And as you can see, it just depends on the slope of the river and the river depth and so on. The other one is another estimate, which is an overestimate, which just says we know the change in elevation between the two gauging stations. If all of that energy ends up as turbulence and all of that is dissipated as turbulence, then we can estimate this quantity there. We expect the top one is a better estimate of the actual dissipation or the actual velocity gradients the algae will experience in the middle of the water column, whereas this other quantity down here is more of an overestimate to give us some idea of what's going on. So now it's time to compare this guy with the algae. So if we just look at the actual river system, so the top chart there just shows the strain rate versus length and time along the Murray River. And you can see that these values decline with distance along the Murray River, so it's becoming more gentle as we get towards the end. That dashed line there is a limit from some laboratory studies looking at the effect of algae survivability based on controlled shear in laboratory settings. And that value there is for some species of algae under some settings, so it just gives us sort of a feeling for when things may start to become a problem. The bottom graph there is for the Macquarie and the Hunter and the Cudgegong rivers there. And you can see, as Lee said, they're quite different river systems. The slopes are much greater. And for the Macquarie River, is again almost twice what the upper parts of the Murray experience. And then the Hunter again is probably 6 times that. So the strain rates are much higher in the Hunter River. And again, if you compare that to what we think is probably a lower, gives you something to compare with, you can see that's really quite a substantial value. Okay, so how do we compare the turbulence with different parts of the algae biovolume? So Yoshi did this analysis. We've just taken 3 stretches of the Murray River and 2 stretches of the Macquarie and Hunter rivers. And so this gives us sections along those most parts of the Murray. These are the sections where not interrupted by lakes or weir pools, and similar story for those other river systems. So we're comparing those, what's happening between those 2 sites. So what is the biovolume at Albury, and comparing the biovolume downstream 2 to 3 days later by the time that same massive algae arrives at that new site. So what Yoshi's done is just compare that biovolume in a time-shifted way. So it's comparing the same populations as best we can do with the field data that was gathered. Okay, and then the difference is just that term there, which is just a logarithm of those 2 things. The travel time between these sites is, they're all about 100 kilometres, and it's 2 to 3 days travel time, except for the Hunter, which was half a day's travel time. So this is really the main result. So we're looking here is a change in algae biomass versus the turbulent strain rate. So this is the strain rate we expect sort of halfway through the water column. And remember, this is a log scale, and you can see there is some kind of a trend. So there's an enormous amount of scatter, and we completely acknowledge that there's many other factors, as other speakers have already spoken about, but there is a statistically significant trend there, and according to Yoshi's statistical analysis, about 40% of the variability is due to that strain rate. So there is a sensitivity there. If you compare the same with this on the right-hand side there, that's for the average turbulent strain rate. So they give the same trend, doesn't matter how we estimate it. The top 2 graphs are just for, we go for Brocade dicholecospermum. I'm an engineer, remember. So one species over there, that seems quite sensitive to it, well, more sensitive to it. The bottom plots show the same thing, but for all the algae species. So if you plot the other 2 species that Lee was talking about there's not really a significant trend. So really this species over there has some sensitivity, but the other species are much less so. All right, so in terms of discussion, both looking at just the direct plots of the algae biovolume along the length of the river, you can see that there is a trend there. Going down the river, there is a decrease. That survivability is greater in the Murray, Edwards and Macquarie rivers, where the slopes are much less. and the geomorphology is quite different as well. In the Cudgegon and Hunker rivers, where the slopes are much greater, the turbulent strain rate is much greater, the die-off is much more rapid. There is this trend with more concentration of cyanobacteria under lower flow rates, and I guess just in terms of a comparison with another benchmark, all the strain rates experienced in the river systems are much higher than the limits we'd sort of expect to see some kind of influence of some species in the lab. In terms of conclusions, we're very, very tentatively saying it supports the turbulence hypothesis for some species, not others. In terms of improving the study, obviously looking at what's happening between the two gauging stations, how the geomorphology changes along the length of the river are all important things. In some rivers, for some species, the die-off may be enough that you could consider this as part of a management plan, I guess, if you've got want to take water from the top of a dam and where the algae is more concentrated, but you know that it's going to die off, then potentially that's an option to consider. I guess toxicity is important in that as well. Okay, so I think I've kept us to time. I haven't had any warning signs. Thank you.
Just a couple of questions with regard to the Dolichospermum and the Mycosis as well. The first part is with regard to algal recruitment from little side tributaries, whether that was considered as a potential source of biomass. And the other one is too, is there any consideration given to the fact that you might have some aconite germination happening with the Dolichospermum?
In the first part of your question, the study was done in most rivers during periods of major droughts, and there was virtually no inflow from tributaries to either contribute other cyanobacterial species or to contribute water, which would dilute the thing. So we think that the bulk of the algae was released from the reservoir and transported downstream with no subsequent effect from tributaries. And what was the second question? No, we didn't look at aconites, although I've looked at other data from the Murray River, and certainly downstream of Lake Mulwala, we have some data that shows that some in-river recruitment does occur, but we didn't really. We weren't really looking at recruitment. We were looking at die-off or potential die-off.
Okay, that was 2 questions, so we're going to leave it there and move on.